Sometimes a solution of a question might look like a magician pulling a rabbit out of a hat. Like the solution comes out of nowhere. And when you see the solution of this, it's going to feel like that, okay? So first, you just happen to calculate the following. 1 over x minus 1 over x plus 1. And it's a question about putting two fractions into one. How do you do that? Well, you need common denominators, right? So you would multiply x plus 1 to the top and bottom of the first fraction. You multiply x to the top and bottom of the second fraction, right? So you multiply x plus 1 here, x plus 1 here, and then over here you multiply x here, and then you multiply x here. Now that you get x times x plus 1 as a common denominator, you're able to put them into a single fraction. It's x times x plus 1. And let's see what is in the top. It's x plus 1 from the first fraction, and minus x from the second fraction. And what is that? That's 1 over x plus 1. Right? Okay. But what does this mean? It means that this function, 1 over x minus 1 over x plus 1, is same function as 1 over x plus 1. Therefore, integrating this will be the same thing as integrating 1 over x minus 1 over x plus 1 dx. And I guess one of the formulas that we'll be quoting over and over again today is that if you integrate f prime over f, what do you get? ln of the denominator, right? So, well, this, we all know that integral of 1 over x is ln of x. But look at the second one. If you differentiate the bottom, you get the top, right? So this is again ln, absolute value of x plus 1 plus c. Done. Okay. All right. But then you would immediately question how one could be able to think of such a thing. Like, for example, let's say you have the second question, and the question looks like integral of the denominator. You have x squared minus 3x minus 4, and let's say you have 5x plus 7 dx. Something like this. Whenever you see a fraction, the first immediate response should be, if you differentiate the denominator, does that give you the top? Because if it does, then you have a very easy question, okay? So you want to look for that one. I might even put one question like that as a freebie, okay? But poor souls who wouldn't recognize will be able to be doing a lot of other things just to get that simple answer, right? Okay, anyways, here, as you can see, if you differentiate the denominator as 2x minus 3, which is not the same as the top, so we have to do something. But it's really hard to think of some easier expression simplifying to what's given. Like this, I somehow knew. So we have to do something called partial fraction expansion for this one. And let me try to give you the idea. First, you want to rewrite this integral so that the denominator is in the factored form. This factored as x minus 4 x plus 1 dx, right? And then you try to ask, okay, what is it? What are those two fractions that would simplify to this complex looking one if you put them together. And the hint is really in the process of getting the common denominator, right? If you had something over x minus 4, and then something over x plus 1, then, well, some people call this cross multiply, but it's not. Cross multiplication is for something totally different. Don't abuse the word. Okay. You really have to multiply x plus 1 top and bottom, not just the top. Yeah. And then for this one, you have to multiply x minus 4 top and bottom. So after making common denominators, you will see that the common denominator would be exactly this left side. Yes?
I didn't hear what you said. Why you put it as a and b? Because like 5x.
Oh, here I was lucky. I knew what the number should be, but
right.
For that one, I have no idea what the number.
You can't tell which one you would put, like 7 as a or like 5 as a.
No, it's just a and b are some constants that I have to figure out. Okay. But I'm actually quite confident that there should be such an a and b, and you would realize that too once we try to put these two fractions into one. Okay, so let's actually do that. We are going to multiply.
I have a question.
Yes.
How come in this case you subtracted them, in that case you added them?
Oh, well, you can think of this. Here we've added 2. This subtraction is addition. Did you know that? Minus 1 is same as plus of negative 1. So it's an addition.
Okay.
Yeah, right?
Like y negative 4 y.
Subtraction is addition, right? Yeah. Okay, so
Oh, because it's 5x plus 7, and then the first one it was just 1? Is that?
no, it's not as simple. Watch me do it, okay? You have to have some patience. Okay, so we're going to put these two fractions into a single thing by multiplying this one top and bottom and this one top and bottom. And now they have the common denominator x minus 4, x plus 1. And then on the top you get ax plus a. And over here you have bx minus 4b. So that, remember, I'm thinking of a and b as numbers. So although they have different letters, these are still thought as like terms. These two terms are still thought as like terms, so I'm going to combine them. Combining would really mean just factoring the x out from ax plus bx, so you get a plus b x plus a minus 4b over x minus 4 x plus 1. Okay. Now you're going to ask, how can this look like what we were given? Now if you compare the two, they have the exact same denominator, same bar for the division, and they have the x, just here's the x, and here's some constant. Therefore, if the following is true, then those two will be equal. If a plus b is equal to 5, right? And if a minus 4b is equal to 7, right? Then, yes?
Is it? Actually, never mind.
Okay. All right. Okay, so if this is true, then that'll be it. That'll be the answer, right? Then if such a and b exists, then the original equation would follow, right? Okay. Now, at this moment, you should be already convinced that such a thing can be done. In other words, you should be convinced that, let me rewrite this completely. Originally, we had a over x minus 4 plus b over x plus 1. You should be convinced that there are such numbers a and b so that these two are exactly the same functions. That can be made to be true because all we need are the conditions that a plus b has to be 5 and a minus 4b is equal to 7. But look, this is a system of two equations, right? With how many unknowns? 2. So does that mean we can solve? Yeah. In most cases, if you have a system of two equations with two unknowns, you can solve. There are some minor cases where the two given equations may contradict each other, but it doesn't happen in this case. So we're going to solve this, and the standard way you solve it is you solve for one variable and you plug into the next one. Or you can just write it like this and observe that you have a here, so you can just cancel by subtracting both sides, right? So a minus a is 0. Negative 4b minus b is
Negative 5b.
negative 5b. 7 minus 5 is 2. Dividing both sides by negative 5 gives you b equals to negative 2 over 5. Okay?
Wait, if you're doing negative 4b plus b, would it be negative?
No, minus. Subtracting. Okay. All right, and then you plug this in here. You get a minus 2/5 equals to 25 over 5. So if you move this to the other side, you get a equals to 27 over 5. Okay, so how does that help us? Well, here's what we just figured out. We figured out that 5x plus 7 divided by x squared minus 3x minus 4 is same as 27 over 5 over x minus 4 plus negative 2 over 5 over x plus 1. And therefore, integrating this side is same as integrating this other side, because they are equal functions. And we can go even further and say, well, this is same as 27 over 5 integral of 1 over x minus 4 dx. And this one is same as negative 2/5 integral of 1 over x plus 1 dx. And they both are f prime over f type. If you differentiate the denominator, you get the top. So this is 27 over 5 ln of the denominator plus, actually minus 2 over 5 ln of x plus 1 plus c. Okay? Now let me make a bit more remark. So you get this idea, right? Partial fraction expansion means you want to express some complex-looking fraction as sum of simpler fractions which are easier to integrate. That's the basic idea. I want to make one more comment on this.
Well, wait a second.
Yes? Oh, you're still writing? It's okay. Because I'm going to show you a better way. How do you get the a and b faster?
Could you just have 5
Okay,
plus
so
x times the...
Here's a tip. You want to multiply. So you have this identity, right? You want to multiply this x minus 4, x plus 1, both sides. Because doing so will kill all the denominators, right? The bad guys, our enemies. The denominators make fractions, and fractions are our enemies. We don't like them. So once we get rid of the fractions, we're happy.
So then you could just set 5x
So
plus
now
7
you have
equals
5x
to
plus 7.
A or B.
A times x plus 1 plus b times x minus 4. Okay, at this point you will probably realize, well, we got this before, right? By comparing the top. However, we want to do something else here. This equality is an equality of functions. In other words, it's an identity. Now, when you have an equal sign, it could mean that it's an identity or a conditional equation. And let me try to explain the difference between the two. So, if you have x plus 1 equals to 2, is this always true?
No.
No, only when x is
Less than 1?
1. No, when x is
Oh,
1,
oh,
of course.
sorry.
1 plus 1 is 2, right?
Yeah.
Yeah, it can't be. Okay, so if you have 1 plus 1 is 2, so x must be 1 in order for this equality to hold. That's called a conditional equality, okay? Conditional equation. And usually when you're given an equation to solve, that means you're trying to find that one value of x or a few values of x that will make the equation hold. Okay? Those are conditional equalities. However, think about the following. If you have like x plus 1 squared equals to x squared plus 2x plus 1, is this always true? This is true for all values of x, whether you plug in 0 or 1 or 2 or 3. If you compare the left side and the right side, after plugging in 1, 2, 3, 4, 5, you always get the same value. Okay? And such an equality is called an identity, or equality between functions. So these two are equal as functions. If you draw the graph of this function, and if you draw the graph of this function, you'll see that they're identical. They always produce the same thing. Yes?
So if you move all the x's to the other side, does it become?
So if you subtract this and if you expand, you get 0 equal to 0, which is always true. So the identity will always have that property, okay?
That's
Yeah.
true.
All right. So once more, what we are looking at is like we want this one and this one to be equal as functions, which means that this must be this must be an identity. It's not a conditional equation, it's an identity. It's true. It has to be true for all values of x. And then you say, oh, okay, so that means whatever value I plug in, this should work. And I plug in x equals to -1. Now, why -1? 1.
Can't spell that one.
Yeah, -1 times 5 is -5 plus 7 is 2. -1 plus 1 is
0.
0, so you get a times 0 plus b times -1 minus 4 is -5, and then you divide by -5, you get b equals to -2/5. Okay, now if you understood why this one worked, tell me what's the other number you want to plug in?
4.
4. If you chose 4, then you're understanding what's our business, okay? Our business model is to plug in something that would cancel. You get 0, so that it's easy to calculate. So if you plug in 4 times 5 is 20, 20 plus 7, it would be 27. 4 plus 1 would be 5, so you get 5a. 4 minus 4 would be 0. So that's what you get. So a is 27 over 5. And it's actually a lot easier than our previous calculation. Okay? So that's the tip. If you do this, then you can get these values quickly, and then you plug them back into this identity, integrate both sides, and there you have the answer. That's how you approach this.